Good afternoon, students. Today we are going to discuss about the vector magnetic potential and the calculation of Biot-Savart's law and Ampere's circuit law using the vector magnetic potential. So let us start our journey of the calculation of magnetic vector potential, or we can say the vector magnetic potential. To calculate the magnetic vector potential, what we are going to do is we are going to consider the potential due to the point charge in electrostatic field, and the expression is given by this 22.1, that is V equals to integration dq by 4 pi epsilon naught r. That calculation of the potential for a point charge in electrostatic field we have derived earlier. Now, keeping in mind this equation, we can write the magnetic vector potential for the line current, which is given by this 22.2. That means here V is replaced by the expression A. Here this A is the magnetic vector potential, that is equals to line integral. Here epsilon naught is replaced by this mu naught. dq is the charge element, is replaced by the current element ideal by 4 pi r. Similarly, like you can see 4 pi small r. So by comparing this expression, or by keeping in mind the potential V, we can write the expression A for the line current. Similarly, for the surface current, just if we change this ideal element by kds, the expression 22.3 becomes the magnetic vector potential for the surface current, and the magnetic vector potential for the volume current is given by 22.4, where also we can see that this current element ideal or IDI is replaced by JDV. Now that equations which we have written, that is 22.2 to 22.4, all the expressions we have written by keeping in mind that the V equals to the integration of dq by 4 pi epsilon naught r. Now we can calculate all these three expressions of the magnetic vector potential for the line current, for the surface current, for the volume current. But here we are going to discuss only one calculation, that is the magnetic vector potential for the line current. For that, we have considered this diagram. Here you can see that the red line is representing a current carrying conductor through which the current I is flowing. Now, in this current carrying conductor, a very small length, that is dl prime, we have taken dl prime, small length. Why it is dl prime? Because the coordinate here we have considered that x prime, y prime, z prime, and the distance of this current element ideal prime from the origin is r prime, vector r, small r prime. Now our aim is to find out the magnetic vector potential at the point x, y, z. So the distance of the observation point from the origin we have considered vector small r. Now the distance between the current element and the observation point is denoted by this capital R, which is equals to smaller minus smaller prime. Now, first point is to find out the magnitude of this capital R. It is very simple to calculate this capital R, which is given by the expression 22.6. Here you see that the magnitude of capital R equals to mod of small r minus small r prime. That is equals to that the x coordinate x minus x prime square plus y minus y prime square plus z minus z prime square whole root. Now, for now, we are going to consider that this grad into 1 by r equals to minus r by r square. That can be proved and we can prove it afterwards. So this value, that is ar by r square, we have seen earlier that this ar by r square is equals to r by r cube, vector capital R by magnitude of this capital R cube. So ultimately, this grad into 1 by r is equals to minus of r by r cube. So finally, what we get from this expression, that r by r cube equals to minus grad 1 by r. Now, in this expression 22.5, if we replace this r by r cube by this expression, then we got that b equals to mu naught into I is the constant current, so we can take it at the outside of the integration. So mu naught I by 4 pi line integral of dl prime cross del or grad into 1 by r. Here you can see that the expression I have written, that again I am repeating, that b equals to minus mu naught by 4 pi line integral of I dl prime cross grad into 1 by r. Now the second step is to apply a vector identity. So the vector identity is given by this expression 22.9, and this vector identity says that grad cross small f into capital F. Here the small f is the scalar quantity and the capital F is the vector quantity. That is equals to small f into grad cross f plus grad small f cross capital F. Now if we consider this small f is a scalar quantity, that means that is 1 by r, capital R, and this capital F is equal to that dl prime, then putting this 1 by r and dl prime in this expression 22.9, we have that grad cross, this small f is replaced by 1 by r, capital F is replaced by dl prime. So this is equals to 1 by r into grad cross dl prime plus grad into 1 by r cross dl prime. Now, if we take this last part of this equation to the left hand side of this equation, and if we change or interchange the position of dl prime and grad into 1 by r, then we have dl prime cross grad into 1 by r equals to minus grad cross 1 by r dl prime plus 1 by capital R into grad cross dl prime. Now this last term will be equals to 0. Now the question is, why this last term is 0? You see that this grad is the differential operator. So this operator works on the point whose coordinate is given by x, y and z. But this dl prime is having the coordinate x prime, y prime, z prime. That is why this term, if we apply the operator on this coordinate x prime, y prime, z prime, this term, last term will be equals to 0. So finally what we get is dl prime cross grad into r equals to minus of grad cross 1 by r dl prime. Now you see that if we consider this current I in this expression 22.8, I is the constant current, so we can take it outside of the integration. So B equals to minus mu I by 4 pi, line integral of dl prime cross grad into 1 by r. So this term can be replaced by this expression. So if we replace this, then the expression of B becomes grad. You can see that here again I am repeating, this minus cancelled out, mu naught I by 4 pi into grad cross 1 by r into dl prime. So after that, if we take this constant term inside the integration and the operator outside the integration, then B equals to grad cross line integral of mu naught I dl prime by 4 pi r. So in this expression, you can see that this term, the grad cross this term, last term, in this expression is denoted by A, and also we have seen earlier lectures that B equals to grad cross A. So we can say that this term, that is line integral of mu naught I dl prime by 4 pi r, that is equals to A. Here we have calculated the value of A, that is the magnetic vector potential for the line current, which we have seen in the equation 22.2. Again, I am showing you this equation. Here you see that the same expression we have calculated for the line current in this expression. This expression A equals to line integral of mu naught I dl by 4 pi r. Now, as we have calculated the magnetic vector potential, so we can represent the total magnetic flux in terms of the magnetic vector potential. How? We know the expression shows that the total magnetic flux psi, that is equals to surface integral of B dot ds, that is the Maxwell's equation. Now B is equals to del cross A or grad cross A. So we have replaced this B by grad cross A. Now if we apply the Stokes theorem, and we have discussed that the Stokes theorem relates the surface integral to the line integral. So we have the surface integral of grad cross A dot ds, that is equals to closed line integral of A dot dl, and finally we got the expression 22.13, that means the total magnetic flux equals to the closed line integral of A dot dl. So I want to tell you that the total magnetic flux can be represented in terms of the magnetic vector potential. Here, 2 points I want to discuss: that the magnetic field can be determined by using the either Vm, that is the scalar magnetic potential, or the vector A, that is the vector magnetic potential. So when we use Vm and where we are going to use A, that depends on the choice which is dictated by the nature of the given problem, except that Vm can be used only in a source free region. Now the one part of our lecture is complete, that is the calculation of the magnetic vector potential. Now we are going to derive the Biot-Savart's law as well as the Ampere's circuital law using the magnetic vector potential. For that, we need to use two vector identities. First vector identities, which we have discussed earlier, this one, that is grad cross F into F equals to F into del or grad cross F plus grad F cross F, that vector identity, and the vector identity grad cross A equals to grad into grad dot A minus grad square A. So these two vector identities we are going to use to calculate the Biot-Savart's law as well as the Ampere's circuit law. Now we know according to the Biot-Savart's law, we know that the B equals to grad cross A. Here A we have calculated, A is the magnetic vector potential, we have calculated that one. So we have written that B equals to grad cross closed line integral mu naught ideal prime by 4 pi r. Now here you see that mu naught I and 4 pi is constant, so we have taken out from the expression, that is integration. So that means that is equals to mu naught I by 4 pi line integral of grad cross 1 by r dl prime, which we have seen earlier in this expression. You see that expression A we have applied, in this expression here A. So now this grad cross 1 by r dl prime, that can be replaced by this expression. Here you see that the expression I told you earlier, the vector identity which we have seen earlier, that vector, according to that vector identity, we can replace that grad line integral of grad cross 1 by r dl, that can be replaced by the expression of this expression. So finally the B, that is the magnetic flux density, becomes equals to mu naught I by 4 pi into 1 by r del grad cross dl prime plus grad 1 by r cross dl prime. Now again you see that the first term grad cross dl prime, that will be equals to 0, because the differential operator acts on the point xyz, not on the point x prime y prime z prime. So we are taking the derivative of this dl prime with respect to the point xyz, that is why it is 0. So if this one is 0, then we can write that B equals to mu naught I by 4 pi line integral of this term, that is del or grad into 1 by r cross dl prime. Now as I told you earlier that we can prove that grad into 1 by r equals to minus ar by r square. Just in this lecture, at the starting of this lecture, I told you that can be proved. Here you can see that this is the simple calculation from equation 22.16 to 22.17. We have proved that grad into 1 by r will be equals to minus of ar by r square. So here this expression grad into 1 by r can be replaced by minus ar by r square. Now if we interchange this expression, then finally we have the B, that is equals to mu naught line integral of ideal prime cross ar by 4 pi r square, which is the Biot-Severt's law, which we have studied in the last class. So it has been discussed that how we can derive the Biot-Severt's law using the two vector identities and the magnetic vector potential. Now, we are going to calculate the Ampere circuit law, which we have discussed in the earlier lectures. And for that, we have taken this vector identity, which we have shown you earlier, that is grad cross A, and grad cross A, that is equals to B. So grad cross B equals to grad into grad dot A minus grad square A. Here this grad dot A, that is will be equals to 0, because it is the Coulomb's gauge. It is called the Coulomb's gauge. In this expression, that grad dot A is the Coulomb's gauge, which is equals to 0. Now if it is equals to 0, then we can write grad cross B equals to minus grad square A. That is written here. You can see that grad square A equals to minus of grad cross B. Here B is the magnetic flux density, which is related to the magnetic field intensity, that is mu naught H. So this B can be replaced by mu naught H. Now mu is the constant term, so you can take it outside of the differentiation. So grad square A equals to minus mu naught grad into grad cross H. So grad cross H, according to the Maxwell's equation, grad cross H equals to J. So finally what we have is grad square A equals to minus mu naught H. Interestingly, the vector Poisson's equation also we can derive using the expression magnetic vector potential. So this expression 22.20 is called the vector Poisson's equation, and the relationship of A and J is also, or it can be represented by this expression. So now this is the vector Poisson's equation. If we want to find out the scalar Poisson's equation, so we have to take the components along the x axis, y axis and z axis. This is given by this expression. Now before studying this expression, another point I want to tell you, that in the case of the electrostatic, we have seen, if you can recall, or if you go to my previous lectures in electrostatics, where we have calculated the Poisson's equation, that is grad square V equals to minus rho V by epsilon. So this expression, if we remember, by comparing this expression, we can also write this expression. You see that grad square V is replaced by A equal to mu naught, that is 1 by mu naught is replaced by, 1 by epsilon naught is replaced by mu naught, and J is replaced by rho V. Here J is the current density and in the electrostatic rho V is the charge density. So we can also by considering this expression also we can write the vector Poisson's equation. Now if we divide this expression 22.20 in the direction of x, y and z, or we can say if we divide into three components, then we have grad square ax equals to minus mu naught jx, grad square y equals to minus mu naught jy, grad square az equals to minus mu naught jz. So this expression 22.21 or 22.21 is called the scalar Poisson's equation. Now again we are going to consider the Maxwell's equation, that is which we have seen earlier, that is the closed line integral of h dot dl equals to I enclosed. So I enclosed we are keeping outside now. So we know that the line integral of h dot dl. So now if we apply the Stokes theorem on this first part of this equation, then line integral to surface integral we can have. So that means we can have that the open surface integral of grad cross h dot ds. Now if we multiply this term with 1 by mu naught, so here I am writing that is equals to 1 by mu naught surface integral of grad cross mu naught h dot ds. So mu naught h is nothing but the b. So here this expression becomes 1 by mu naught surface integral of grad cross b, that is dot ds. Now b equals to grad cross a. So here again we have 1 by mu naught surface integral of grad cross a dot ds. Now vector identity, we have this expression. Earlier I told you that if the grad dot a is the Coulomb's gauge which is equals to 0, so from that we have calculated earlier that minus grad square j, that is equals to mu naught j. So we have that the line integral of h dot dl here, that line integral of h dot dl, that is equals to 1 by mu naught surface integral of mu naught into j. Mu naught cancel out. So we have that surface integral of j dot ds, and here j is the current density. So surface integral of current density if we take, we have the current. So this line integral of h dot dl, which is equals to I enclosed, which we have studied earlier, that is the Ampere's circuit law. So what we have studied here, that the calculation of the magnetic vector potential. After calculating the magnetic vector potential, we have derived the Biot-Severt's law as well as the Ampere's circuit law using the magnetic vector potential. So thank you very much students. Today we are concluding here. See you in the next class. Thank you very much for attending my class.